At 3:14 p.m., a quantum physics lab becomes the site of a deviation in the flow of time. The environment appears routine. Cooling fans hum in the server racks, and researchers monitor the steady progression of data across their screens. A heavy ceramic coffee mug slides from the edge of a desk, drops, and shatters violently against the tile. A researcher pushes through a heavy security door, which swings shut with a mechanical click. At precisely 3:14 and 8 seconds, every clock in the facility stops. Reality resets to the first frame of the sequence. The mug is back on the desk. The researcher is back in the hallway, opening the same door again. Outside the facility, the world moves forward normally, but inside the lab, the researchers retain their memories of every 8-second cycle, transforming a few moments of clock time into what feels like years of repetition. Of course, this scenario is a thought experiment. No group of scientists has ever been trapped in a macroscopic time loop. The narrative is built on a real discovery in quantum mechanics regarding how matter behaves when it is pushed out of equilibrium. Physicists found a way to make matter repeat itself in time, mimicking the logic of a loop on a subatomic scale. In 2012, a Nobel Prize-winning physicist proposed that our understanding of crystals was incomplete. He theorized a state of matter called a time crystal. Standard crystals, like diamonds, are defined by spatial symmetry. Their atoms lock into a repeating 3D grid. A time crystal breaks this symmetry. Instead of a static spatial pattern, its atoms move in a rhythmic cycle through time, returning to their start continuously. The initial proposal faced immediate, heavy resistance from the scientific community. A system that moves forever without any external power source looked exactly like a perpetual motion machine, which most physicists agreed should be physically impossible. Because it challenged thermodynamics, many dismissed the theory as a mathematical curiosity that could never exist. Several years later, a small number of laboratories attempted to build the structure using trapped ions and quantum bits. The experimental data showed the atoms oscillating at a specific frequency that remained stable, regardless of the energy being put into the system. The results confirmed the hypothesis. Scientists had created the first physical time crystals. These structures maintain their internal ticking indefinitely. They remain in constant motion while staying in their lowest energy state, meaning they never run out of movement. This success demonstrated that matter can spontaneously break time translation symmetry, a behavior previously thought to be impossible. In a contemporary lab, the focus is on a much smaller scale than our opening thought experiment. The endless loop is actually occurring right here, suspended within a vacuum, down at the level of individual quantum particles. Time crystals are now recognized as a phase of matter that remains stable outside of thermal equilibrium. Researchers are now moving past the discovery phase and looking for ways to utilize this stability. This repeating pattern may protect quantum information from decoherence, making time crystals a potential candidate for the memory systems of future quantum computers. We moved from a controversial paper in 2012 to a physical reality in less than a decade. If the laws of physics allow for matter that repeats itself through time, we have to consider what other science fiction concepts are currently waiting for a laboratory to prove them real.